Welcome to the deep dive. Today, we're digging into something I think a lot of developers face: refactoring really complex code bases. You know, that feeling of being kind of lost in code you might have even written yourself.
Exactly. And if you're listening in, maybe feeling a bit overwhelmed and wanting to get up to speed quickly, think of this as, well, your shortcut. We're boiling down the essentials from some really practical guides on how to make this whole process more manageable.
Okay, so let's clarify. Refactoring. It's not just chucking everything out and starting over, is it?
No, definitely not. Martin Fowler's definition is pretty much the gold standard here. He calls it a controlled technique, applying a series of small behavior-preserving transformations. The key thing is behavior preserving. You're changing the inside without changing the outside.
Small steps, keeping it working. Got it.
Right. It's like renovating a house room by room, not knocking the whole thing down. The cumulative effect of these small changes can be huge, but each step is controlled.
So our mission today is to really understand the practical side of this. How do you actually do it? Why bother? And how do you approach it smartly? The sources seem really focused on that practical angle.
They are, and they highlight a common problem right away. Refactoring often gets delayed. It's seen as, well, not an immediate business need, maybe, until things get really bad, like you can't add features or the team's just completely bogged down.
Yeah, that sounds familiar. Which brings us to the big why, right? If the code technically works, why invest all this effort?
Technical debt. That's the core concept. Codes that maybe worked fine initially can, over time, become this tangled mess. It works, sure, but making even small changes becomes incredibly slow and, frankly, risky.
So technical debt is basically the future cost of taking shortcuts now, or just letting things degrade.
Pretty much. It's why that simple bug fix suddenly takes 2 weeks instead of 2 hours. The past decisions are catching up with you.
It's like not doing the dishes. Eventually, the sink overflows. But okay, if it's so obviously a problem long term, why does it always seem to get pushed down the priority list?
Well, the sources point to the usual suspects. The pressure for new features, urgent bug fixes that are visible, client demands. These things have immediate deadlines and visibility.
Right.
Refactoring feels less urgent, even if it's important.
Short-term wins versus long-term health, that classic tension.
Exactly. And the challenge is shifting that culture slightly, not necessarily stopping all new work that's usually a mistake, but building in time for maintainability, finding that balance.
So how do you get, say, management on board? How do you make the case that this isn't just developers wanting to play with code, but something the business actually needs?
You've got to tie it directly to business outcomes. The sources give good examples here. Things like refactoring this module will let us launch the new analytics feature X% faster, or cleaning up this area will reduce outages by Y%, improving customer satisfaction.
So less, we need to clean up the code, and more, doing this enables that specific business goal.
Precisely. Frame it in terms of speed, stability, future capabilities. For instance, refactoring the reporting engine unlocks our ability to build that crucial analytics module next quarter. That connects the dots for everyone.
Makes total sense. Translate the tech need into a business benefit. Okay, so let's say you've made the case, you've got the go-ahead, you're looking at this beast of a code base. Where on earth do you start?
Right. The first absolutely critical step, according to all the sources,
Yeah.
build your safety net. And that means automated tests before you change anything.
You need confidence that you won't break things silently.
Exactly. You need to know immediately if a change has unintended consequences.
And that's where things like characterization tests come in. I saw that legacy calculated discount example. That seemed useful for code you don't fully understand.
It's incredibly useful for that scenario.
Hmm.
Characterization tests don't check if the code is correct according to some spec you might not even have. They check what it currently does. You write tests that capture its existing behavior, warts and all.
So you're documenting reality before you try to change it.
Precisely. If you refactor and the behavior changes, even slightly, those tests fail. It's your baseline.
Okay, so that covers the legacy stuff. But the guides also mention unit tests, integration tests, end-to-end tests. Why the whole suite?
Because they test different levels. Unit tests check the smallest pieces in isolation. Integration tests check if those pieces work together correctly. And end-to-end tests check entire user journeys through the application.
So layers of protection.
Exactly. The more coverage you have at these different levels, the more confident you can be that your refactoring hasn't broken something important.
And the final piece of the safety net was the CI pipeline, the continuous integration. That .github workflow.iml file looked technical.
Let's think of it like the automated quality control checklist. That file tells the system every time someone pushes new code, run all these tests automatically.
Ah, so it forces the testing to happen constantly.
Right. You get feedback within minutes if your changes broke anything. It builds confidence and catches regression super early, which is vital during refactoring.
Okay, safety net check. Automated tests running automatically. Now, how do you decide what to refactor? You can't boil the ocean, right?
Absolutely not. The goal is to focus your effort where it matters most. Look for the problem areas, the code that's complex, error-prone, slow, or just a major bottleneck for development.
So be strategic. Don't just refactor for the sake of refactoring.
Definitely not. And the sources offer several ways to find these hotspots.
Like what?
Well, sometimes the simplest way is best. Just ask the team. Developers usually know exactly which parts of the code are painful to work in. The magic wand question is great for this. If you could magically fix one part of this code base, what would it be?
Ha, I like that. Taps into that gut feeling and experience. What about more data-driven methods? Complexity metrics were mentioned.
Yeah, tools like SonarQube can analyze the code for code smells. Things like really long methods, huge classes, duplicated logic, super complex if else chains, they often calculate metrics like cyclomatic complexity.
Which measure?
Basically, the number of possible paths through a piece of code. High complexity often means it's hard to understand, hard to test, and probably buggy. The tools flag these complex areas for you.
Okay, so complexity is one indicator. What else? The sources mentioned churn.
Right, churn or change frequency. Look at your version control history, hit get, SVN, whatever. Which files change the most often? Especially which files are changed frequently alongside bug fixes.
Ah, so if a file is constantly being tweaked, especially to fix bugs, it's probably fragile or poorly designed.
Exactly. It's a strong signal that the code isn't stable and could benefit from refactoring.
And then there were combining those two ideas, complexity and churn.
Yes, that's hotspot analysis. Tools like CodeScene specialize in this. They find the code that is both complex and changes frequently. These are your prime targets.
Because fixing those gives you the biggest bang for your buck, right? You're improving difficult code that people are actually working on all the time.
Precisely. Fixing these hotspots can dramatically reduce bugs and speed up future development in those areas.
Makes sense. And the last category was performance bottlenecks and crashes. That seems pretty obvious.
Yeah, if a part of the system is slow or keeps falling over, that's clearly a priority for investigation and likely refactoring.
Okay, so we've used these techniques. We've identified a gnarly piece of code we want to improve. What now? The guides talked about isolating it first. Why?
Because in complex systems, everything's connected, often too tightly. That problematic module probably talks to 10 other things. If you just start changing it, you risk breaking those other 10 things in ways you didn't expect. Isolation minimizes that blast radius.
So how do you isolate it? Michael Feather's idea of seams came up.
Right. A seam is basically a place where you can change behavior without modifying the original code directly. Often this means introducing interfaces or abstractions. The payment service example was good.
Where it directly depended on the Stripe gateway.
Exactly.
Yep.
By introducing a generic payment processor interface, the payment service now depends on the interface, not the concrete Stripe gateway. Then you create a Stripe adapter that implements that interface.
Ah, so you've put a layer in between. The service talks to the general idea of a payment processor, and you can plug Stripe or PayPal or whatever into that adapter slot.
Precisely. It breaks the direct dependency, isolating the payment service from the specifics of Stripe. Now you can refactor or even replace the Stripe implementation without touching the payment service.
Okay, that makes sense for isolating dependencies. What about that branch by abstraction technique? Sounded a bit more involved.
It is, yeah. It's often used when you need to make a bigger change while keeping the system running. You create an abstraction layer over the existing code. Then you build the new refactored version alongside the old one, both sitting behind that abstraction.
So you have both the old and new code living side by side for a while.
For a time, yes. The abstraction layer can route calls to either the old or the new implementation, maybe based on a configuration flag or for certain users. You gradually shift traffic to the new version.
Like a dimmer switch, slowly turning up the new and turning down the old.
Exactly. It lets you test the new implementation in production carefully and roll back easily if needed. It's related to the strangler fig pattern, gradually replacing the old system piece by piece.
So the key is focusing on the high-impact areas, that may be 20%, causing 80% of the pain, and then using these techniques, interfaces, abstractions to wall them off before you start major surgery.
That's the essence of it. Reduce the risk by limiting the scope of potential problems.
All right. We've identified the target, we've isolated it. Now for the actual refactoring work, incremental versus big bang, that seemed like a key strategic decision. The process order function example highlighted this.
Absolutely. Incremental refactoring means making small, verifiable changes. You take that big, messy process order function and maybe extract one piece of logic into its own small function, test it, commit it, then extract another piece.
Keeping the system working after each tiny step.
Right. The advantages are huge. Lower risk, easier to find the source of any new bug you introduce. You can stop and deploy at almost any point, and development can continue alongside it.
Whereas the big bang is trying to rewrite the whole thing at once.
Pretty much. A major overhaul, often taking weeks or months, where the system might be broken or unstable until the very end. The guides are generally very cautious about this approach.
Understandably, when would a big bang even be considered?
Maybe if the underlying technology is completely obsolete and has to be replaced entirely. But even then, the advice is usually to try and break that massive rewrite into smaller, phased releases if at all possible.
So the strong recommendation is go incremental whenever you possibly can.
Overwhelmingly, yes. Treat large refactorings as a series of small, manageable ones.
Okay, let's talk about a specific kind of beast, the monolith. Lots of systems end up this way. The guides mention challenges like being unwieldy, slow builds, changes causing ripple effects.
Yeah, monoliths can become victims of their own success. As they grow, managing complexity becomes really hard. How do you start untangling that? The guides suggest modularization strategies.
Like separating layers, UI, business logic, data access.
That's a classic one. Even within the monolith, just logically separating those concerns helps a lot. Makes it easier to understand and modify parts without affecting others as much.
What about splitting things by business function?
That's domain-based modularization. You identify distinct business areas like accounts, orders, products, and e-commerce, and structure the code around those domains. Each module should handle its own area well, with clear boundaries and APIs connecting them.
Trying to make modules that are focused internally but loosely coupled externally.
Exactly. High cohesion, low coupling, even within the monolith.
And then there's the bigger step, extracting services or microservices.
Right. This is a major architectural refactoring. You physically pull out parts of the monolith into separate, independently deployable services. Great for scaling and team autonomy, but adds the complexity of a distributed system. The strangler fig pattern is often used here too, gradually carving off pieces.
But there was also a middle ground mentioned, the modular monolith.
Yeah, that's becoming quite popular. It's structuring the single application into well-defined internal modules with really strict boundaries and interfaces, almost like internal microservices, but without the separate deployment and network calls. It gives you a lot of the organizational benefits with less operational overhead.
Interesting. Kind of best of both worlds sometimes.
It can be, yes. When breaking down a monolith using any of these approaches, the key things are maintain functionality throughout, ensure backward compatibility, and test relentlessly. And be prepared for team workflows to change.
Okay, let's dig into that backward compatibility piece. That seems critical, especially if other teams or external systems depend on the code you're changing. How do you avoid breaking those contracts?
It's a huge concern. You absolutely have to preserve existing contracts,
Yeah.
APIs, data formats, config files, anything that something else relies on. The SendMail example showed this well.
Right, you created a new internal SendB2, but kept the old SendMail signature working, maybe by having it call the new one.
Exactly. The public interface remains stable. You can then mark the old function or API endpoint as deprecated.
Giving people a heads up that it's going away eventually.
Yes, and providing a clear timeline. For external APIs, explicit versioning is common a P of one something and a P of two something exist side by side during the transition. A clear deprecation policy is essential communication.
What if the data itself needs to change? New database schema, different message format.
That's where adapter layers come in handy again. You might write code that translates data between the old and new formats on the fly, allowing new code to work with the new format while still understanding or converting data from the old format when needed.
To a temporary translator during the migration.
Exactly. And again, testing specifically for backward compatibility is non-negotiable. You need tests that explicitly verify the old contracts still work as expected after your changes.
Makes sense. Another big challenge, dependencies and tight coupling. When everything's tangled together, changing one thing breaks 5 others. How do you loosen those knots?
The goal is modularity, right? Making components more independent. Introducing interfaces or abstraction layers is key, like we discussed with the payment processor. The order service and order repository example showed this too.
Where the service depends on the order repository interface, not a specific database implementation.
Precisely. That's dependency inversion. It decouples the high-level logic from the low-level details. Dependency injection is another powerful tool here.
Where dependencies are passed in rather than created internally.
Right. This makes testing way easier because you can inject mock dependencies. You can test the order service without needing a real database, just a mock order repository.
And what about facades?
Facades are useful when you have a really complex subsystem with lots of internal parts. A facade provides a single, simpler entry point to that subsystem. Other code interacts with the easy-to-use facade instead of getting tangled in the complex internals. Reduces coupling significantly.
So interfaces, dependency injection, facades, all ways to create cleaner boundaries between different parts of the system.
Exactly. They make the code easier to understand, test, and change safely.
We keep coming back to testing. It feels like the bedrock of safe refactor.
It absolutely is.
Yeah.
You cannot refactor complex code safely without a solid testing strategy. It starts with establishing that baseline regression tests, characterization tests for legacy code like Feathers talks about. Get that safety net in place first.
Capturing the current behavior before you touch anything.
Yes. And then continuous integration is crucial to run those tests constantly as you make changes. Get that immediate feedback.
And for deploying the changes, things like canary releases or feature flags.
Those are about reducing risk in production. Canary releases expose the refactored code to a small percentage of users first. Feature flags let you turn the new code on or off easily in production. Both give you a way to roll back quickly if problems occur.
Plus performance testing if that's a concern, and maybe things like approval testing for tricky legacy areas.
Right. It's about using a combination of testing techniques at different stages. Development, integration, deployment to build maximum confidence.
Now, one fear people sometimes have is that making code cleaner or more abstract might make it slower. How do you refactor without hurting performance?
That's a valid concern. Ideally, refactoring shouldn't change external behavior, and performance is part of that behavior. But yeah, sometimes it can inadvertently be affected.
So what's the advice?
Be mindful, especially in known performance-critical areas, and crucially, .measure. Use profiling tools, like the C-profile example, before and after refactoring.
Don't guess. Get data.
Exactly. Profile the code, make your change, profile again. See if there's a regression. Treat performance like any other functional requirement you need to preserve.
And the guides mention refactoring can sometimes even improve performance.
It can. Removing duplicated work, maybe improving caching by consolidating logic, simplifying complex algorithms. These things can sometimes lead to speed-ups as a side effect of making the code cleaner. But measurement is key.
Okay, one last area the guides touched on, which feels very current. Using AI for code reviews. How does that fit into refactoring?
It's an emerging helper, really. AI tools can automate some parts of the code review process, like checking for style consistency, identifying common code smells, or catching potential bugs based on patterns.
So they can handle some of the routine checks.
Yes, freeing up human reviewers to focus on the bigger picture, the architectural choices, the logic itself. Tools like CodeRabbit were mentioned.
What can they do specifically?
They can provide contextual feedback right in the pull request, suggest fixes, summarize changes, which is great for large refactors, even allow chatting with the AI to understand suggestions. Some IDE extensions offer similar features too.
So it's like an assistant helping to maintain quality and spot potential issues during the refactoring process.
That's a good way to think about it. It can boost the workflow, enforce standards, and potentially catch things earlier, making the whole process smoother.
Wow. Okay. We've covered a lot of ground. From the why and getting buy-in through testing, identifying hotspots, isolating them, the actual strategies, monoliths, compatibility, dependencies, performance. It really is a whole process.
It absolutely is.
Yeah.
But the core takeaway, I think, is that it's about small, controlled steps. It's an ongoing investment, not a one-off panic fix. Like tending a garden, you have to do it regularly to keep things healthy.
Comparing it to renovating a building without disrupting the occupants earlier felt right too. Continuous improvement.
Exactly. Making it part of the regular development rhythm is the key to preventing that massive, scary technical debt from accumulating in the first place.
Right. So a final thought for everyone listening. Maybe think about one small process or habit in your own work. Could be coding, could be anything, where a little bit of refactoring, a small controlled improvement might make a surprising difference.
Yeah, applying these principles of identifying issues, making incremental changes, and checking the results. It's a powerful mindset that goes way beyond just code.